Hi everyone, it's Albert again, co-director of this year's national tournament. As you know, running a Science Olympiad national tournament is no easy feat, and it requires a great team with people like Spiros, who I have here with me here today. Spiros is a mathematical physicist at the Institute of Quantum Information and Matter, and also serves as the outreach director. Thanks for taking the time to speak with me today, Spiros. Can you tell me a little bit about what you do here?
Yeah, sure. First of all, Albert, I think that what you do here is a Herculean effort, like putting together the national tournament, working non-stop with your team. I think it's very impressive. That's why I'm very happy to always support these efforts. Outside of some, of the work that I do with you on Science Olympiad, I do research and then outreach. So as part of the Institute for Quantum Information and Matter, I have the opportunity to study some very fundamental aspects of the quantum realm. Anywhere from how do we build scalable quantum computers to where does space and time come from. So there's some of the deep things that everyone here at the Institute for Quantum Information and Matter gets to study, and it's very exciting because this generation that is watching this and the next generations are actually going to have the toolkit to manipulate things at the quantum level, which is something that was considered science fiction until very recently. And in fact, this is exactly what I bring to the outreach that I do, where I go and work with Hollywood, like Marvel Studios, and then I introduce elements of this quantum realm, these powers, into the movies like Ant-Man, Ant-Man and the Wasp, and then Captain Marvel.
I see. So I know quantum is like a really hot topic in today's science field. Can you tell us more about what quantum means and what your research is like?
Yeah, so quantum is pretty powerful. Usually we think of quantum as the theory of physics at the most microscopic level, where you have the ability as a particle to be at two places at the same time, right? To be able to travel back in time. The rules that we're used to kind of fall apart down at that level. And what we're trying to do, again, here at Caltech and universities and labs around the world is to try to blow up to our macroscopic human scale some of the superpowers that you can find within the quantum realm.
Oh, that's really cool. Now, you brought up Marvel, and I'm a big Marvel fan, and I'm sure many of our viewers will also be Marvel fans. So can you tell us what that advising role is like?
Yeah, so I got a call from Marvel Studios about 7-8 years ago now, 2014, and Paul Rudd needed some help as one of the writers, actually, not just the star of Ant-Man. And he wanted to know what happens when you go microscopic, when you go very small, like size of an ant, you want to understand the physics of it. But when I got there, I guess I convinced them that they should go way smaller than an ant, at the level of atoms and below, and that at that level you have quantum properties like superposition and entanglement, which then end up making the second movie, Ant-Man and the Wasp, as well. And I remember telling them, down at that quantum realm, right, the source code of reality, you can manipulate things, and if you know how to do this, you may be able to actually change the very fabric of space and time. You may be able to time travel in ways and teleport. So a lot of the things that superheroes, the powers that they have, when you have different stones, right, the Tesseract, the Power Stone and all these ones, they have their powers drawn from within quantum physics. And that's why they were very excited, and the quantum realm has now become a big part of the next phases of the Marvel Cinematic Universe.
That's really amazing, and I'm so glad we can bring topics like quantum into movies and stuff that more people can see. One last question. I know you've been our club advisor for a while and have been a strong supporter of Science Olympiad since the beginning. When we started here, basically. Do you have any final advice for the competitors as they go into competition day, or maybe as they go into college as well?
I think first of all, it's impressive that you have made it, as far as you have made it, with this determination, perseverance. You have school, and on top of school, you're doing something amazing like that. This is very impressive. Consider just in your future, continuing to have fun like this. You can do hard things, deep things, but if you take it slow and enjoy the process and make friendships that can last lifetimes, then you will be like Albert at some point, right? You'll continue giving back to that community because it was such a big part of your life.
Thanks so much, Spiros. All right, that wraps up our time with Spiros today. Thank you so much for taking the time to speak with us, and we'll catch you soon.
Good luck, everyone.
Bye. Hi, everyone. We're back today with Professor Hunt. Can you introduce yourself for us?
Sure. Hi, I'm Melany Hunt. I'm a faculty member in mechanical engineering at Caltech.
Awesome. Thanks so much, Professor Hunt, for taking the time to speak with us today. Can you tell us a little bit about what you do here?
So I've been a faculty member here at Caltech for more than 30 years. And it's a combination of doing research work with students, so either graduate students or undergraduate students, and then teaching classes and working with students in terms of special projects or other things that they're interested in doing. My work in mechanical engineering is really in the area of fluid mechanics. And so I've worked on problems that aren't just fluids, it's also often problems of fluids and particles. And so it's different than just thinking about flow over an airplane wing, that a lot of the problems that I think about are flows where you have other stuff in that flow as well. So things like debris flows or slurries or suspensions where you've got a fluid plus you've got a bunch of particles.
This sounds really interesting. Can you tell us like a little bit more about that fluid flow thing? Are there any like kind of real world examples that you can relate that back to?
There's lots of real world examples actually. Any kind of powder that you might think about flowing, so even things like sugar or salt, it flows actually very differently than a flow of a liquid. That you can have a pile of the material build up when you're emptying your salt shaker, and occasionally you might see an avalanche of that material. And again, if you were just doing the same thing of pouring out a liquid, of course your liquid would just continue to spread. But with something like a powder, you could actually get a pile of material and then occasionally the avalanche. So the kinds of processes that we think about in these flows are similar to what you might think about if you've got a debris flow, so a whole release of material down a hillside. Or you might think about these kinds of problems when you think about a sand dune, and you think about the avalanching in the sand dune, or other kinds of problems in terms of handling these kinds of materials that you probably, as you're driving around, you might see a big pile of sand or a pile of dirt. And what we are interested in is just, how do you manipulate that and how do you predict the flow, when it flows and when it doesn't flow. It would be one of the things that we're very interested in.
Awesome. And I guess that research will be useful for loading for boom lever and for towers when we have to load our structures. So
it's probably the same kinds of things as thinking about those tower kinds of things that you might think about.
Yeah. Well, I wanted to ask, so how did you get involved in this sort of research, and why did you decide to pursue it and continue teaching here at Caltech?
So it was related to some of the things I did before I started came to Caltech, but it's actually a field where there actually are lots of applications, but not so many people doing the research work, so we could do a lot of interesting things that were new. One of the things, if anyone's interested in looking, we've done a lot of things with sand dunes over the years, what's called booming sand dunes. And in certain places in the world, a sand dune can make actually a loud noise, and it can actually sound like a cello. And so these are on very large sand dunes. And what you need is kind of a natural avalanching on the surface of the sand dune. And the dune itself generates this sound that really can be a very clear frequency, so it really can sound like a musical instrument. So it's one of the projects we've done actually over many years with both undergraduate students and graduate students, and take a lot of people out to the desert. But if you go online and look under booming sand dunes, you'd probably see some of our videos that we've done with National Geographic or with PBS or with NOVA, just about interest. Those groups have just been interested in how this all happens and what kind of scientific explanation can you get for a sand dune sounding like a musical instrument.
Oh, that sounds amazing. And for our competitors, we'll make sure we put a video link or something in the description for you to look at that more. Can you tell us why you chose to come here at Caltech?
Well, when I was looking for jobs, Caltech was actually looking for faculty, so it was a good time to be looking. So I finished graduate school, and really I started at Caltech, and I've been here ever since. But Caltech, it was interesting for me because Caltech is a very different institution, that it's small and just focused on science and engineering, which I found really attractive. It gives me a lot of opportunity to interact with students, to have kind of small groups of individuals that I can interact with either through class or through various kind of projects. And yet there's a lot of collaboration among the faculty and collaboration among different research groups, which is really attractive.
That sounds exciting, and I know from the student experience I can definitely relate to how collaborative the school is, and it's one of the main reasons I came here, so it's awesome.
Again, I think what students always say, it's much more about collaboration than competition at Caltech.
For sure. Here more than anywhere else, I remember too. That being said, there is a competition coming up. It's the national tournament, obviously. Do you have any words of advice for competitors?
Well, what I'd tell any student in any situation like this is don't get discouraged. It's easy for, especially if you're doing experimental science, it's easy to have things not work right away. Again, in terms of the competition, do your best. If it doesn't quite work the way you want it to work, please don't shy away from it. Take it as a challenge. Work on whatever didn't work right the first time, and hopefully you stay in the field. There's lots of exciting things that can be done in science, engineering, mathematics, and what we like to see are more students pursuing these fields.
That's awesome. So really wise and encouraging words from Professor Hunt. Thank you so much for tuning in for this episode. Thank you so much for taking the time to talk with us today, and good luck on competition day.
Good. Yeah, good luck.
Right.
Absolutely.
All right, bye. All right, hi everyone. Welcome back to our STEM Expo. Today we have Dr. Jessie Christiansen. Dr. Jessie, would you mind introducing yourself for our viewers?
Hi everyone, I'm Jessie. I work at IPAC on the Caltech campus. You probably haven't heard of it. It stands for the Infrared Processing and Analysis Center, and it's where NASA does a lot of their public data archiving and processing and releasing of data.
I see, that's very cool. I noticed some interesting history to IPAC and its relationship with JPL. Can you tell us more about that history?
Sure. So JPL, which is just up the road from IPAC, is where a lot of the really interesting rocket propulsion stuff was happening in the 50s and 60s. And it was very secret. There were fences and people with guns. It was all very under lock and key. And then when NASA data started to come out and they realized they wanted NASA data to be public, they were like, well, it doesn't actually need to be behind all of these fences and people with guns. So they came down to Caltech campus and they started this center, IPAC, this Science Data and Analysis Center. So we serve all of NASA's public data from many of its missions.
That's really awesome. And so can you tell us more about your role within IPAC? Do you do research? Do you manage data? Do you do a mix of both? Can you tell us more?
Yeah, so I actually really love my job here. So I'm a research scientist at IPAC, which means I spend 50% of my time supporting the NASA project that I work on, that I'll talk about, and 50% of my time doing my research. There's another track here at IPAC for scientists called the Staff Scientist track, which is an 80-20 split, so 80% of time supporting a science project and 20% doing your own research. And people like those different tracks for different reasons, but I really love the research. So the project that I support is the NASA Exoplanet Archive, and this is how NASA keeps track of all of the exoplanets we've found, which are planets outside our solar system. And so far we've found over 5,000.
Wow.
So what the archive does is keep track of how many we found, anything we know about them, their temperature, their size, where they are, what kind of star they orbit, for everybody to use in their science. My research part is I like finding planets, so I use NASA's missions like Kepler and K2 and TESS to actually search for planets around other stars. And luckily enough, I get to find some, and then they go into the archive.
Wow, that's really cool. What's like the coolest thing you've seen? I can imagine like finding exoplanets must be like an amazing thing. Do you have any like particular cool stories or cool facts you've seen here?
Well, so one of my favorite systems that I got to be very lucky to lead the discovery of is called K2-138. I'm going to stop now and apologize. Exoplanets have terrible names. I'm very sorry. I don't actually get to name them. There's a rule we have to follow, and it's a garbage rule. Anyway, so the system is called K2-138. The reason I love it so much is it was found by citizen scientists.
Oh.
So people at home on their computers looking through NASA data. So my colleagues and I set up this citizen science project on a website called Zooniverse, which hosts many citizen science projects, where we served Kepler data and we were like, help us find the planets in these data. Because we write software to search the data and look for planets. But when we're writing software, we're making assumptions about what it's looking for and what the data look like. So the computer does a really good job of finding that exact thing. But stars do all sorts of interesting things, and planets do all sorts of interesting things. So what's very difficult to do is tell the computer, look for something surprising, look for something weird, look for something that stands out. But you can tell a human brain to do that pretty easily. Like we show you what a signal looks like and then go to the data and say, hey, what do you see? And people see everything. They're like, what's this? What's this? What's this? It's like the face in Mars, but in Kepler data.
Wow.
So they found this system, and I was lucky enough to, be part of this project and help turn that system into a confirmed system. Now has 6 planets in it, and citizen scientists found, I think, all 6. So that was really, really marvelous to be part of, and so exciting to get to include the citizen scientists on my paper as co-authors.
Wow, that's actually crazy. So I imagine this is something that people of a lot of ages can do. It's not just people with PhDs and stuff. So.
Yeah. So the whole point is, in 2 minutes on the website, we show you what a planet looks like and what it doesn't look like, and then you just go. And then, honestly, it's as much time as you can devote to it. So we have test data right now. This is NASA's Transiting Exoplanet Survey Satellite mission called TESS. And data are coming down from TESS every 2 weeks. So if you go to planethunters.org, which is our TESS citizen science project, you can actually start looking for planets right now.
All right, so maybe our competitors can do this, but after the national tournament day, maybe not quite beforehand. But yeah, that sounds like a fun opportunity. So I wanted to ask, because I know a lot of people might have the image of, getting into research as like this one track of like going undergraduate, graduate school into PhD, having to do academic research at a university, or that's it. Now it sounds like your work is a little bit different and your pathway is also a little bit different. Can you tell us about that pathway?
Yeah, so, growing up in a small town in Australia, I had no idea about academia and universities and that kind of thing. So when I got to university, I had no idea what kind of job you could do in astronomy. And that was when I started to discover that there are all these different careers you can do just, starting from a degree in astronomy. So working, for instance, at a government institution, doing program support and doing your own research is one of those things. You can also work at observatories, for instance, being telescope operators and doing that kind of thing. Or you can work on what we call soft money, which is where you apply for grants and then you pay yourself to do the science that you've promised to do. That one's hard, but some people can make it work if they write convincing proposals. And then the last one is becoming a professor at a university and doing your own research. So there are lots of different things you can do to have a career in astronomy. And that's just research related. There's all these adjacent things like science communication and instrument building and science policy. There's lots of really interesting astronomy adjacent jobs as well, not just being a professor.
It's cool that there's so many fields and ways of getting into research and science, no matter who you are. I guess our final question is, it's almost competition day, and middle schoolers and high schoolers across the nation, they're probably going to be listening to this. Do you have any final words of advice for them?
Have fun. This is so exciting, and I'm so proud of all you guys for making it to this. What an opportunity. So, meet people and have fun and really just enjoy the day.
All right. That was Dr. Jessie Christiansen. Thank you so much for taking the time to speak with us today, and good luck to everyone. Bye.
Bye.
Hi everyone, welcome back. I'm so glad to be here talking to you today, and this is my professor, Karthish. He currently teaches me in Chemie 103C here, which is a transport class. But I recently found out he's actually a Science Olympiad alumnus too, so we figured we had to speak to him. So Karthish, thanks so much for talking to us today. Can you tell us a bit about what you do here?
Yeah, absolutely. So I started here at Caltech as a faculty member in chemistry and chemical engineering just last year. I was a faculty member at MIT for 5 years before that, but got very excited about getting to be part of this community here at Caltech. We're a really small group of researchers who work together in a very collaborative and interdisciplinary fashion to make progress on what we think are some of the toughest problems of our generation. We figure out the science first, and we hope that that science then creates a pathway towards having impact on the world. My own research group works specifically on taking renewable electricity and using that to convert air and water into useful molecules. So imagine if we could make the fabrics of our shirt, or even components of the chair that we're sitting in, using just air, water, and sunlight, instead of using petroleum, which is often the feedstock that goes into making the physical world.
Oh, I see. Can you tell us a little bit more about that process of how you get, things from air into actual products we can use, and what was the thought process that went into it?
Definitely, yeah. So I think a lot of what this involves is designing catalysts. Catalysts are these entities that are able to grab onto molecules, bind them to their surface, and then rearrange the chemical bonds that exist in those molecules. So we start with CO2, nitrogen, and water. We take those design catalysts that will bind them and scramble the bonds to then make molecules we care about. These are molecules like ammonia, or making an amino acid, or making ethylene to make plastics, all from just CO2, nitrogen, and water. Really, our source of inspiration, this is nature. Nature actually already does this. We are not able to do this abiotically without nature. So we're trying to find new pathways to do this without a living system and to be able to power it all using electricity, since we have this new opportunity where renewable power is so much cheaper than it used to be. And that's really what we're driving forward in our lab, with science and making catalysts that manufacture the physical world sustainably.
Got it. And it's really fitting that we're in the Resnick Institute of Sustainability. It's over there. Changing gears a little bit, I heard you were a Science Olympiad competitor. Tell us about your competition days.
I was. Actually, it was my very first opportunity to go from very traditional textbook learning in a classroom where a teacher told me what I was going to learn in a given day, and I'd go home and do the problem set and come back and I'd take an exam. I'd grown very used to that ritual, and I really needed something to help make me feel more excited about going to school. And I remember finding Science Olympiad, and I remember being told that I was going to be on this event called Dynamic Planet. And I had to go and learn about this broad field that was huge. There were so many different aspects and topics that went into Dynamic Planet. I no longer had someone telling me what I had to know. I remember going to the library and taking 20 books off the shelf and struggling to carry these home, and then starting to page through these and deciding how I was going to study that material. And the reason that's important is that to me represents open-ended inquiry. It's what it means to learn by yourself, self-directed learning. And that for me has been now the majority of what I do on a given day as a faculty member or working with my students. It's teaching them how to think and how to learn something when someone isn't telling you what to learn, right? And so Science Olympiad was sort of my first journey into open learning, and so it was a very special opportunity for me for that reason.
Got it. So hopefully this will get released a few days before the tournament. Do you have any advice for competitors who are maybe watching this right now?
Yeah, so there was this event called Robo Billiards that I remember competing in. It was by far the event that I put the most time into. I would stay up late at night building this robot. Weekends, I worked around the clock trying to build this thing. And the real challenge for me was that I built something that I thought was functional, that I thought should work, that I thought should be competitive, that I thought should win. And I went into this competition. I remember setting it down on this table, competition day. It was the state tournament in Texas. And we start the event, and we start moving this robot, and boom, one of the contacts snaps off. And when the contact snapped off, that was it. That wasn't something that I could have planned for or that I could have anticipated. It just happened. And that for me is one of the biggest lessons that I learned in this, is that you do something like this that's risky, you do something like this that involves something that could fail, and it could fail for reasons that are outside your control. And so we ended up ranking at the very bottom. We were the last team out of all that competed, even though this thing I poured all my time into. And I remember, like, for a long time after that, it bothered me. It bothered me that I had failed at this, that I had done the poorest of any team that had entered this competition, despite putting so much time and love into this. And I had to learn that I couldn't just look for this external validation. I wanted that external validation so badly going into the competition. But I had to learn that a lot of this wasn't about what someone else thought about me. It was what I am learning in this process. It was the love that I had shown to this subject, how I had grown as a person through this, and to place value on that, and to know my own true intrinsic enthusiasm and excitement for something, that was enough. That is all that I needed from this. Now, I still seek internal validation sometimes. I'm not free of this force, but learning my own internal compass and knowing what I do in my life because I need it and I want it has been so important for me professionally and personally. And I think Science Olympiad was sort of one of those first times where I had to learn that for myself.
I see. All right, well, thanks so much. That was really inspiring advice you gave. And I know for me personally, Karthish is one of the most inspiring profs that I've had here. So I really want to thank you for spending the time to talk with us today, and hope, the viewers can learn something more about Caltech and about you.
Awesome, and I just want to thank Albert, and obviously there's an amazing team of people here at Caltech that are throwing this competition, putting in countless hours and sleepless nights to make this event what it is. I just want to thank them as well for making this opportunity possible for everyone coming in.
Thank you so much, Karthish. All right, we'll see you in the next episode. Bye. Hi everyone, welcome back. Today we're going to meet another amazing member of our faculty here, Professor Emami. Professor Emami, so you can introduce yourself?
Sure, hi. My name is Azita Emami. I'm a professor of electrical engineering and medical engineering at Caltech. I'm also the executive officer for electrical engineering, which means head of department.
Oh, that's amazing. Can you tell us more about what you do here? Like, what's your research like?
So we work on electronic and photonic systems for a variety of applications. One of the domains that we are very interested in is medical devices. So my students and my researchers work on developing very tiny wireless devices that can go inside the body, or we can implant them in the brain to learn more about the body or to monitor patients. Also, we work on wearable devices that we can monitor the health.
Wow, I see. Sounds like a lot of cool stuff. And I know like one phrase that's been kind of thrown around by students around here I've heard is cell silicon, and I heard that's from your lab. Can you tell us more about what that means?
Yeah, that's a cool project that we started in collaboration with Professor Richard Murray. He is in biology and biological engineering at Caltech. So the idea is to create systems that can interface electronics with cells and biology, and create a system that has two-way communication between electronics and biology, so that we can do a lot of processing in electronic domain, and we also do some level of control and processing in the biology domain.
Nice. And this sounds really fascinating. How did you get involved in this field?
So I actually, my background is in electrical engineering, so I started in domains that are more traditional to electrical engineering, like high-speed communication systems. For instance, in data centers, we need to move data very fast at hundreds of gigabits per second. So I still work in these domains, but I realized that because the goals of those projects are to implement sophisticated circuits like tiny chips and also reduce the power consumption, the goals match very well with biomedical devices, where we need tiny devices that are very energy efficient, and they have a lot of capabilities, and they can sense, they can communicate. So I transitioned gradually from that field of more traditional electrical engineering to biomedical engineering.
Got it. I know you mentioned a lot that they're very low power and very small. Could we check out one of the cells? I kind of want to see what it's like.
Yes, we can go to the lab, and I can show you one of those tiny chips that I just talked about.
Yeah, awesome.
All right, so let me show you an example of one of the chips that we designed in my lab, and my graduate students worked on this. So this is a tiny, tiny chip that is in the middle.
Oh, wow.
And the image of it is shown here. So as you can see, it's about maybe 1 millimeter by a couple of millimeters, so it's very small. Right now it's in this package so that we can test it. But eventually this can go into very tiny ingestible capsule that a patient can take. And this device has the capability of sensing certain biomarkers. So for instance, if there is inflammation, then it can help to deliver the drug accordingly with the exact amounts that we want based on the measurements that are made. And this is a fluorescence-based measurement. So the chip that you can see here, you see all these beautiful colors.
Right.
These are metal layers on top of a chip that has been designed in a way to filter out certain light wavelengths and only let through the target wavelengths that we are looking for in a fluorescence sensing system. That's why we call this a cell silicon project, because we are interfacing silicon real-size systems with the biology and with cells and proteins that we want to measure or sense.
I see. So maybe each of these colors is like a different sensor or something?
Yeah, there are different filters that can sense different fluorescence proteins.
Oh, I see. And one final question I'm thinking, so is that powered by itself? Like you can just take the medicine and it'll figure it out by itself?
That's a great question. So we have chips that actually harvest energy from the body itself.
Oh.
So we have that capability. This particular chip doesn't have that capability, but in the future we can add it. But it's very, very low power, so we can add a tiny battery in a capsule. And then because it comes out of the body, so that's no problem. But that's a big challenge in many of medical devices, how to power them up. Sometimes we power them up wirelessly with a radio frequency signal, and sometimes we harvest the power like a biofuel-based system. We use the existing biomarkers in the body to use them as a biofuel and power up the system. And sometimes we incorporate a tiny battery. So depending on the application, we power them up in different ways.
Got it. That sounds so cool. I didn't know you could use your own body to power cells like that. Thanks so much for taking us into the lab.
Of
Really
course,
awesome.
my pleasure.
All right.
Yeah.
All right, so competition day is almost coming up for our competitors. Do you have any final advice for them?
I hope that they always maintain their confidence, their enthusiasm. I'm sure all these students in this competition are very hardworking, and that's essential in the future for them as well, to be curious, to be fearless, and thirsty for learning new things. And I wish all of them a fantastic tournament. I hope they enjoy coming to Caltech and being part of this amazing competition.
All right, and thank you so much, Professor Emami, for taking the time to speak with us today. And that wraps up this episode. I'll hopefully catch you soon. Bye.
Bye-bye.